So next property is related to the derivative of a Laplace transform. Thing is that it's going to work on the derivative of complex functions, which we haven't really done yet, and that I don't think we will have time to do it that here. But anyway, let's do it. Let's give it a few details because, as we said, I don't think we're going to have more time to deal with complex functions, holomorphic functions, that is, at the end of the year. So we have this theorem that tells us that the Laplace transform of a function is holomorphic on its domain of convergence. Is holomorphic inside of its domain of convergence, and I know you don't know what holomorphic means, but we're going to say that very soon, of its convergence domain. So there's a whole calculus that we can do on complex functions, and actually it's a bit different than what we can do with real functions. So let's just give some details about that. So holomorphic, what does it mean? It means differentiable in all directions at all points. In all directions at all points, because you remember there's something quite similar to the functions on R2, that if you have some point x, y defined in R2, and maybe that's x plus I times y, that defines also a point in the complex plane. If you want your function to be differentiable at that point, it means that for any direction that you use to converge to that point x plus iy. So let's say that this is point z0 in the complex plane. You get that the limit as z tends to z0 of the growth rate, that's f minus z0, z minus z0, is the same value whichever the way you use to converge to z0, okay, whatever the direction you use in R2, and that is what we will call f prime of z0. Okay, so there are many properties, very specific properties linked to holomorphic functions, and that's a whole study topic in itself. But well, we will just need this, and we will just need the results of this derivative. In that case, we also have that the derivative of the Laplace transform of a function, okay, that is going to be given by this formula minus Laplace transform of t times f of t applied to s. Okay, and actually with this formula we can do many things, and this formula and the other one that goes together with that one. Okay, so we should do some proof. We haven't done any proofs in a long time, so we all miss that. Okay, right. So let's first write what we have. So our aim is to write something like that. Okay, the limit of the growth rate. So let's write that. We have Laplace transform of some function f is obviously going to be given by the usual formula, e minus s times t. Now, if instead of s, I want to do a small increase of s in the complex plane, that's what is that changing. That's going to be f of t, e minus s plus h times t dt. Okay, so this is actually equal to I can factor with f of t, e minus h times t, e minus st dt. Of course, okay, and let's see, and of course, what we have. Let's see what it gives us, okay? And I want to compute I want to compute the limit of the growth rate that is written a bit above. So I want to show that the limit as h tends to 0 of the difference between L what of f of s plus h minus LF of s divided by h, okay, minus, well, what I want to obtain is minus Laplace transform of t, f of t applied to s, okay, and I want that to prove that this is converging to 0, okay, as h tends to 0. Is that true? Okay, so let's write what we have for the first part. So we'll want to take the limit of that following thing. I'm not sure writing the limit stuff. So I get that that's going to be the integral, okay, from 0 to plus infinity of, what do I get? This here minus that here. So I can probably factor with a lot of things. I'm going to get f of t e minus st times, so I've got e minus ht minus 1. Okay, so e minus he coming from here, the minus 1 coming from the fact that I've got nothing else here, and we should divide this by h dt. Okay, plus, well, that's coming from the two minuses here, so I write the formula, integral from 0 to plus infinity t f of t e minus st dt. Okay, so we have to compute this, and I can go on and put everything under the same integral. So integral between 0 and plus infinity, f of t e minus st. So what do I have then? E minus h times t minus 1. Sorry, the minus 1 is on the same level as the exponential, minus 1 over h plus t dt. Okay, now if I want to compute the limit of, as h tends to 0, of the modulus of all this, okay, right. What do we have then? I'm going to make, as usual, that it's going to the modulus of the integral, well, or the absolute value or modulus of the integral is smaller or equal to the integral of the modulus. So that's it. So I've got f of t e minus s t times, well, this stuff here, e minus h t minus 1 over h plus t dt. Okay, but then actually, if you look at that, what do we have? That's exactly the first order Taylor expansion of e of minus h times t around 0, of e of h times t in a neighborhood of 0. Neighborhood of 0. Okay, what do we get? This is we get that e of minus h times t is equal to the value in 0, so e of 0, which is 1, plus the derivative of e of minus h times t, that's just going to be minus h times t times exponential of minus 0, so that's again going to be 1, all right, plus some order 2 of h2t2, right? So what do we get? We get And so what we have is exactly this thing divided by h. Okay, we have e of minus ht minus 1 over h plus ht divided by h, so that's t times exponential of 0. Okay, so this is exactly what we have. And also divide this by h, so that actually that whole thing here is going to be small o of h2 over h, so that's h times t squared. So which means that it does go to 0, well, as h tends to 0, that really goes to 0. Okay, so what do we have actually is that the last thing we need to do is to exchange the limit. Let's have a look back. We want to get the limit of that thing is going to be equal to the integral of, I want to be able to write that the limit as h tends to 0 here is still valid, but as it is behaving as exponential of minus t, we took all the precautions in order to be able to apply the usual theorems and to say that, well, our integral is going to be converging, so there's going to be no problem about this. I really hope then that finally the limit as h tends to 0 of that whole stuff is 0, and we really get that L of f of t, so the derivative of that is given by minus the Laplace transform of t times f of t applied to s. Okay, and actually you can even get further by induction. Okay, what would you get? The second derivative would be minus L times t times f of t differentiated. So what do we get? We will get that. For instance, let's do the second one so that we know what we're doing. S prime, that second derivative, that would be minus the derivative of minus L of t f of t of s, but that's just going to be, I want to differentiate that again, okay? That's the derivative of the first derivative. So what we're going to get, we get minus, let me write it this way, minus 1 to the square, L of, I have to multiply by t again, my previous function, that's going to be t squared, f of t of s. So that was just the second step, but you could do a clean induction to show that actually if you want to compute the nth derivative of your Laplace transform, you're going to get minus 1 to the n L of t power n of f of t of s. Okay. The good thing about this is that it's an equality, and don't forget a very important fact, sorry, that equalities are two-sided. What do I mean by that? I mean that by this same formula, I will be able to use actually the fact that the Laplace transform of t times some functions that I already know the Laplace transform of is actually going to be, well, minus the derivative of the Laplace transform of f. Okay, that's how you see this. You can see this formula in the other way. Example, we already know that Laplace transform of the Heaviside function was 1 over s. Okay, let's now compute the Laplace transform of t, the t function, t times h of t. Okay, well, according to this formula, that's going to be minus the Laplace transform of h applied to s differentiated, so that's minus 1 over s derivative, that's minus 1 over s squared. With a minus, that's 1 over s squared. Okay, and so on. If you want to compute L of, sorry, L of t square, h of t, you're going to get minus the derivative of the previous one, which would be minus 2 over s3, so that's 2 over s3. Okay, so finally you get by induction L of t to the n, h of t of s is going to be given by, well, if you lead the formula to the end, n factorial times divided by s power n plus 1. Okay, so just we computed one single Laplace transform. We did the h of t, and that led us to get all the exponentials and also the trigonometric hyperbolic trigonometric functions, and now we get all the monomials. Okay, so that's quite a lot of functions that we already have, and actually we could, well, let's do some more. We still need to find the normal trigonometric functions, and we're going to use other properties. Okay, next property is also one of the very important properties, well, assume that you've got, so that's a theorem, assume that you've got f that is differentiable and continuously differentiable on 0 plus infinity. Well, 0 could be included, doesn't matter. Then on its convergence domain, we have that the Laplace transform of the derivative of f is going to be equal to s times the Laplace transform of f minus f of 0. And please take the time to apply it to the second derivative. So maybe pause and try to compute this one by yourself using the previous formula. Okay, so what do we get when we're doing that? Well, that's we get that it's s times the Laplace transform of f prime minus f prime of 0. But I also know that the Laplace transform of f prime is going to be s times the Laplace transform of f minus f of 0 minus f prime of 0. So what do we obtain? We get s square Laplace transform of f of t applied to s minus s times f of 0 minus f prime of 0. Okay, that's the Laplace transform of the second derivative. Let's do a quick proof of that. You can train on that by yourselves, by the way. So again, feel free to pause the video. Let's compute that. Otherwise, okay, so let's write what we have. Sorry, that's going to be the integral 0 to plus infinity f prime of t e minus st dt. What do you feel like doing when you see that kind of thing? Well, of course, you all want to use IBP. So we put u is equal to e minus st, u prime, that's going to be minus se minus st. V prime is, of course, f prime. V is f. So if we apply the formula, that's going to be f times e minus st. So that's f of t, of course. 0 and plus infinity. Minus minus, that makes a plus. S integral 0 plus infinity of f of t e minus st dt. And this is Laplace transform of f of s. First thing, in plus infinity, well, we said that that is, we assume that f had at most um, an exponential growth, so that, and even we can define then the domain of convergence of the Laplace transform such that this is going to go to 0. Okay, and in 0 it's just going to be, well, f of 0 times s times 0, this which is 1, which is 0, and exponential of 0 is 1. So that's going to be minus f of 0 plus s times Laplace transform of f of s, okay, which is the formula that we wanted to find. Okay, so let's use this. We want to compute the Laplace transform of the sinus function without doing explicitly the integral, of course, because we are very lazy, as this is what characterizes people doing math. So let's apply those formulas. All right. So let's say that I know that cosine is actually that sinus is actually so let me rewind the formula that we get. We know that L of f prime is s times L of s minus f of 0. So I know that sinus is actually, so this is where I'm going to put my sinus, is the derivative of, well, minus cosine. Okay, so let's write my formula here. Minus cosine. So L of sinus of t is going to be equal to s times L of minus cosine of t s minus, so that should be f is going to be cosine of 0, which is actually equal to 1. Okay, and so that's minus, I because of linearity, L of cosine of t of s minus 1. Okay, but now I can use that cosine is itself the derivative of the sinus. Okay, so that's going to be minus times s times L of sinus of t applied to s minus the sinus in 0, which is 0. Okay, minus 1. Okay, so what do we get? We get that L of sinus of t on the left-hand side is equal to minus s square L of sinus of t on that side, and that's going to be oh, I did some error. It's going to be minus cosine of 0 here. Sorry, I've modified my stuff here. That I had forgotten a minus cosine of 0, because that was my minus cosine of 0. So that makes a plus 1, that makes a plus 1, and that I still have a plus 1. So here I've got plus 1. Okay, so now I can solve my I can put L of sinus of t of s times 1 plus s squared is equal to 1, so that the Laplace transform of the sinus function is equal to 1 over 1 plus s squared. Okay, that's another formula. If you have time now or later, don't forget to do that. That could be the first exercise we can do. Compute using the same formulas, the Laplace transform of the cosine of t. Okay. Next, we're going to have some theorems about. Well, first of all, we get a corollary of this one. Corollary. It tells you that the Laplace transform of a primitive function. Okay, so that would let's relate it to what we have earlier. So the primitive function is on that side. So, and we said it's the primitive function that is equal to 0 and 0 because we wrote it as the integral between 0 and t. So that would be equal to 0. And I just have to take the other side. So instead of a derivative, as I chose the primitive as f, I'm just going to have the usual function, but I will have to divide by s. So let's sum that up. That is just going to be 1 over s L of f of t of s, okay? Because that's the primitive when we write it this way, equal to 0 and 0. All right. Okay, next thing is going to be dealing with limits.